Welcome everybody. Today I will talk about thermal conductivity of micrometer scale materials to introduce our new instrument, so-called periodic laser heating. And before I will start, just some organizational informations. All participants are muted, but you can always ask questions via the chat function of the webinar. And at the end of our presentation, I will answer your questions. In case of any problems, just use the comment function of this webinar and I will try to help you. Our webinar will be recorded and you will receive an email with a link to the recording afterwards. Also, please feel free to give us feedback to the webinar afterwards so we can improve ourselves. Before we come to the actual webinar, I would like to introduce myself briefly. I am Sebastian Vollner and I studied physics at the University of Bayreuth. Here at Linzais, I'm responsible for several development projects, especially in the field of thermal transport. And you can always contact me if you have a question which is specific in the development field. So please feel free to contact me by email. So here you can see our agenda of today's webinar. My presentation will start with a little general introduction of our company. Then I go further to explain you the principal theory of our LFA, our laser flash analyzer, to build a bridge to our new measuring technique, so-called periodic laser heating, PLH. And afterwards, to differentiate them more, I will teach you where are the differences between them both. And later I will show you some more measurements of this technique. And afterwards, you will gain more insights to our application fields, to our other instruments like the LFA and the TF-LFA for thin films. And then you will learn the benefits of our new instrument, the PLH. And to conclude the talk, I will explain you the specifications of our new instrument. Just to start, Linzais Messgeräte GmbH was founded in Selb in Germany in 1956 by Dr. Maximilian Linzais, who is shown on the left picture. Today, the company is led by the second generation Klaus Linzais and the third generation Florian and Vincent Linzais, which are also shown in the pictures. Next to its headquarters in Selb, Germany, Linzais has own subsidiaries in the US, as well as China and in India. Furthermore, Linzais has representatives and customers all over the world in more than 65 countries. So as you see, we are everywhere worldwide. So if you have a problem, someone from us can come to you and help you. You see in the bottom a picture of our old data logger, which was sold in the beginning of the country, but nowadays this product isn't in our product line, it's sold by a different company. Also, the main business area of ourselves are the manufacturing of measuring instruments for thermal analysis, thermal conductivity, and thermal electrics. Linzais also own a service lab to which you can send samples which will be measured for you. The product range includes a complete lineup for analyzers such as differential scanning calorimetries, thermal balances, simultaneous thermal analyzers, which is a combination of DSC and thermal balance, dilatometers, thermomechanical analyzers, instruments for measurements of thermal conductivity and thermal diffusivity in the bulk, as well as for nanometer thin materials, for which our thin film analyzers is used. We also offer instruments for the characterization of thermoelectric materials, and last but not least, custom-made instruments, which can vary from little changes to more sophisticated modification. For instance, most of our instruments can be coupled to gas analyzers, such as mass and infrared spectrometers, or be put under high pressure for detailed research. Our new instrument will nearly close the gap between the bulk and the nanometer thin film analysis for the thermal conductivity and thermal diffusivity. So let us start with the theory of the LFA. Its schematic explanation is shown on this slide, and the most important parts are the power source, which is a neodymium YAG laser, which is used to heat up the backside of a sample using a very short heating pulse. And this energy of the pulse is absorbed by the sample. Afterwards, a thermal wave propagates through the sample to its rear side, where this thermal energy is emitted via radiation in the infrared range. This infrared signal is detected by an infrared detector as a function of time. And as you see, a signal like this can be seen in the detector, and out of this signal you can calculate its time, which is required to reach the half of the maximum temperature, the half-time rise. And out of this time and the thickness of the sample, you can calculate the thermal diffusivity with this basic formula. So the thermal diffusivity is 0.13879 times the square of the thickness of the sample through the half-time rise. To optimize this process of finding the half-time rise, Linzai's software package offers several evaluation methods. To imagine you the setup of our LFA a little bit better, I have here prepared your schematic side view, which illustrate the most important parts of the instrument. So again, let us short walk through the essential steps of a measurement. For that, we start from the bottom of the drawing. There you can see the light source for the generation of high intensity pulses. In our case, it's a laser or a xenon lamp. The pulse hits the sample, heats it up. The sample emits the thermal energy again, and this thermal energy is detected by a detector. The detector and its belonging corresponding electronics evaluate this data, and you see measurements like this. It can vary really large. Some samples are really thick and slow, and the measurement times are really long, like 25,000 milliseconds, which is 25 seconds. This is for a sample which is in the polymer range and is really thick. Otherwise, your sample can be really thin and metallic, which is a high conducting material, and then your measurement times are really short, like 45 milliseconds. As you can see, it really depends on the sample, how long the measurement will take and how long it takes till the halftime rise is till the temperature rise is completed. So what matters is the ratio between the thermal properties, thermal diffusivity or thermal conductivity, and the thickness of the sample. And this will result in the measurement times. This experimental setup works really good as long as the time scale for the measurement is not too short. But the higher the thermal diffusivity of your sample gets and the thinner the sample gets, the bigger the measurement error gets. The classic laser flash technique runs into two main limitations. The first one is the problem to acquire enough data points within the short time period of the experiment. And the second one is the overlapping of the heating pulse on the backside with the temperature rise on the front side. As you see on the right side, a good measurement is displayed. The temperature rise is after the pulse. The LFA is sufficient. You gain a good measurement result. But what happens if the situation changes and the temperature rise of the sample is too fast and the overlap with the laser pulse? Then it would result in poor measurement results. And the LFA wouldn't be enough for your application. But here at Linsize, we are now offering a different approach to surpass this limitation. And we call it periodic laser heating. So let us jump to a little theory of periodic laser heating. What you see here is a schematic explanation of the periodic laser heating setup. What has changed compared to the laser flash analyzer, and basically the heat source and the detection. The heat source or light source is now a modulated laser, which emits continuous amplitude modulated laser light. This energy is then absorbed by the sample and induces a thermal wave in it. This thermal wave has one similarity to the modulated laser. It's the frequency, and it is pretty clear because it was generated by the modulated laser light, and so it's also modulated. The thermal wave propagates through the sample to its rear side, where the absorbed energy is then emitted. So you see, so the detector sees infrared modulated light. And as you see below, a schematic scheme will illustrate this. You see here the modulated laser light, which is symboled with EL, and the infrared radiation, which is displayed as ER. As we know, both are oscillating with the same frequency. But here it will be clear that there is a phase shift between the two periodic signals. And also this is really clear because it has to be a phase shift between the excitation and what comes out of this excitation. This phase shift and the amplitude of the infrared light is then detected by a lock-in amplifier. The measurement is then taking place by varying the frequency of the laser and recording the phase and the amplitude. This results in characteristic plots for phase shift and amplitude, which looks like this. So you change the frequency and record the phase shift and a kind of amplitude and plot it versus the square root of the angular frequency, which is a kind of a frequency. Out of these plots, you can determine your thermal diffusivity by these equations. So the thermal diffusivity is then the square of the thickness of the sample divided by 2 times the square of the slope of the linear range of these curves. Because we have 2 curves, we combine them and gain the thermal diffusivity by the equation below. It's then the thermal diffusivity of the sample is the square root of the product of these 2 parameters. But what are now the main differences between the LFA and the PLH? In both cases, we subject our sample with a thermal disturbance. But in the case of the LFA, the sample is subjected by a short, high-intensity laser pulse. On the other hand, in the new instrument, the PLH, the sample is subjected by a periodic thermal disturbance. Furthermore, this disturbance is then deserved as a function of frequency, which means the evaluation is in the frequency domain. On the other hand, the LFA evaluates the signal as a function of time. So you see, it's in the time domain. Also, the typical measurement range of a LFA is in the millimeter scale, while the typical measurement range for the sample thickness of the PLH is in the micrometer range. The advantages of the classic LFA are the short measurement times, the broad measurable range of thermal conductivity, as well as the broad temperature range. But the evaluation is a little bit tricky. It can be complicated and there are many different fit models. The main benefits of the PLH measurement are the possibility to measure very thin freestanding films. And in addition, it's a pretty model-free evaluation. You just have to find the most linear range of data points, and then you can calculate your thermal diffusivity. But on the other hand, you have to count with a little bit longer measurement times. And at the moment, our measurable temperature range is limited. But I think now you will ask you why we then need to measure thin films instead of just bulk samples. Thin films behave different. The physical properties of thin films are different from bulk material because of different effects. For instance, the parasitic surface effects are much stronger due to the smaller dimension and higher aspect ratio. That means that the surface plays a much bigger role than the bulk material. And the weight of this influence depends on the thickness of the sample and the volume to surface ratio. If we have a look at a simplified model, we see that the phonons or charge carriers can move in any direction in a 3D body. But if you go to a quasi 2D body, the movement is restricted. And out of this restriction, you get different physical properties for thin films than for bulk material. Another important point is sometimes you cannot produce a sample thick enough to measure it with a classic LFA. So it's just too cost intensive to produce it like that. So then you have to measure thin films. And what thin film samples look like are shown on this slide. There you can see different samples which are measured by our PLH. On the top left is a coated and uncoated PTFE foil, polytetrafluoroethylene, or better known as Teflon. In this case, it's 100 micrometer thick, and it's pretty clear that it bends a little bit, but it doesn't matter because our sample holder will bend them down. In the middle of this picture, you see a 25 micrometer polyethylene foil, PE. As you see, one is coated and one is uncoated, but the uncoated on the top is barely seeable because it's so thin. And that's why I put it on a blue background to see it a little bit better. So to imagine, the measurable samples are really, really thin. But to enhance the signal, you have to coat your sample, and this is made by a standard carbon spray, which is displayed in the right top of this slide. This coating is needed to increase the absorption and the emission of the sample, so your signal gets higher and your results are better. In the top, in the lower left, sorry, in the lower left corner, you see one of our sample carousels with an equipped sample below. If you look in the right bottom, there is a close-up view of one of our samples within a sample holder. So there you see the sample is really plain in this sample holder. So let us jump to a little bit interesting part where I show you some of our measurements. First, start with a little bit clarification of the pictures. How you read the measurements. On the y-axis, the phase shift in radians or the converted amplitude is displayed. While you see the square root of the angular frequency on the x-axis. In the right top of the pictures, you can see the result of the measurements. And the thickness of the sample and the fit quality. So as you see here, as an example, polytetrafluoroethylene again, with a thickness of 50 micrometer, and the expected value for the thermal diffusivity of Teflon is 0.11 millimeters square per second. As you can see, our measurements yields exact this value, and the repetition of the measurement reproduce this value very precise. So it's a very nice measurement. And if you double the thickness of the sample, the thermal diffusivity of Teflon hasn't changed. It's still around 0.11 millimeters square per second. And as you can see, our measurement still stands this value. If you repeat the measurement, it's still very precise, and the value is in the range of the measured thermal diffusivity. The next example is another freestanding polymer foil, polyethylene, with a thickness of around 25 micrometers. What we here expect is a thermal diffusivity in the range of 0.15 to 0.90 millimeters square per second. So it really depends on the polymer. what we get is a value perfectly in this frame. And like before, if you rerun the measurement several times, the value has hardly changed. Our next example belongs to the category of ceramic materials. It's a sapphire, a well-known material, and in our case, approximately 500 micrometers thick. And its thermal diffusivity should be around 13.3 millimeters square per second. And what we expect is what we get. The measurement curves are good, the fit is great, and the evaluated thermal diffusivity is nearly exact the value we should measure. Again, the repetition of the measurement is quite good, which is displayed on the right side. So you see, it's still the value you expect. Last but not least, here's an example of a really, really thin sample of copper, a metal with a high thermal diffusivity of 117 millimeters square per second. Moreover, our instrument could even handle this difficult sample and extract the correct value of the thermal diffusivity of the copper sample really good. And also the repetition is quite okay, I think, for such a thin sample. To give you a little bit more illustration about the application field, here is a roughly estimation what is possible for our thermal conductivity analyzers. It is displayed the application field for the laser flash analyzer, the periodic laser heating, and our TFLFA. But you have to pay attention that the axes are scaled logarithmically. So you see that each segment on the axis means a step by a factor of 10. A logarithmic scale is helpful if you want to picture very small and very large values in one chart, which is here presented. So you see, the LFA is more suitable for thicker samples. Our latest development, the PLH, is better for thin films in the micrometer range, while the TFLFA is the better solution if you want to measure really thin samples in the nanometer range. To give you a little bit more insight what such materials are measurable, I pictured you a little bit here. PTFE, Teflon, like we've seen before. YSZ, it's yttria stabilized zirconia, which was formerly used for tooth crowns, but now is used for not metallic knives. What are the benefits of our new invention? The Linsize product lineup is now with more possibilities. You can combine the LFA and the PLH in one system, in one common hardware. And if you combine these two measurement instruments in one, that's you get a measurement instrument with a vast measurable range. And also this combination is patented, and you cannot see it anywhere else. It's a unique combination which offers you a unique measurable range. So this upgrade is possible if you have a new LFA analyzer, or if you buy a periodic laser heating setup. So if you buy one of them in the beginning, you can upgrade it with the other one afterwards. So you don't have to choose of buying both in the beginning. To sum up the talk of today, I want to show you the specifications of the PLH and the combination of the PLH. So first start with the PLH. It's intended for the measurement of freestanding films, membranes, and more. Also, you can automatically measure your samples and measure up to 6 different samples automatically, depending on their dimensions. Furthermore, depending on the thermal diffusivity of the sample, you can measure the samples down to a thickness of 10 micrometer and up to a thickness of 500 micrometers. Also, the standard temperature range is up to 300 degrees Celsius. The maximum CV power of our laser, which is included in the system, is up to 5 watt and is automatically checked by the software. Furthermore, the evaluation of the measurement is pretty model-free. And if you buy a combination of the LFA and the PLH, your possibilities increase vastly. And the specifications expand too. Like before, you can measure freestanding films and membranes, but then but in addition, you can now measure solids, liquids, pastes, powders, and PCMs, phase-changing material. Like before, you have the option to automatic sample throughput, which means you can measure the samples automatically one after another and up to 6 different samples. Depending on the thermal diffusivity of your sample, you can measure the samples with a thickness in the range of 10 micrometer to 6,000 micrometer and up to 2,800 degrees Celsius. Your light source is now equipped with an intensive short pulse with up to 25 joule per pulse or CV light with a maximum power of 5 watt. And also our advanced evaluation can evaluate your measurement data independently of the used measurement technique. So thank you for your attention.